In the last video, we looked at reacting ethers with haloacids, and in those reactions, we were using an Sn2 mechanism because we were dealing with situations where the carbon-oxygen bond of the ether was not sterically hindered. In other words, the carbon-oxygen bond was at a carbon that was a primary carbon. Now what we're going to look at instead are situations where the carbon that's bonded to the oxygen is in a more sterically hindered environment, which forces the reaction to undergo an Sn1 mechanism rather than an Sn2 mechanism. So what we're going to be looking for here are situations where the carbon-oxygen bond, that particular carbon, is a secondary carbon, a tertiary carbon. This will also apply if the carbon that is bonded there is allylic or benzylic. And as a reminder of what we mean by allylic and to let you know what benzylic means, allylic refers to a situation where we have a carbon that is bonded by a single bond to an alkene group. So this is our allylic carbon, would be the carbon at the far left in the structure I just drew. This carbon right here is our allylic carbon. So if we have an allylic carbon, that's going to favor undergoing the Sn1 type mechanism because it can readily form a carbocation. Same thing or similar thing if we have a benzylic carbon. A benzylic carbon is one that is adjacent to an aromatic ring. So it's the same sort of theme that you have a carbon directly bonded to an alkene group connected by a single bond here, so that there will be some resonance stabilization of a carbocation that would be formed at this position, at the benzylic position, which I'm circling here in this molecule, or the allylic position, which I'm circling here in this molecule. Benzylic specifically refers to its being bonded just outside the aromatic ring. Allylic refers to any situation where you have a carbon that's connected by a single bond to an alkene group. So let's go ahead and take a look at the mechanism for this Sn1 type reaction. And we're going to focus, as our example, on what I have highlighted in gray here, where we are reacting diisopropyl ether with 2 equivalents of hydrogen iodide, HI there. So let's go ahead and do that. So in our mechanism for this reaction, we're focusing here on the mechanism. There'll be Sn1 because we're looking at secondary or tertiary carbons or carbons that are allylic or benzylic that are bonded to the oxygen. In our case, for our specific example here, we're going to do this molecule reacted with HI. And the first step of this mechanism, anytime we have a relatively strong acid reacting with an organic molecule, look for protonation as the first step. We're looking for a site that we can protonate within the organic molecule. Specifically, that oxygen atom with its lone pair of electrons is a great place that can come over, attack the proton of HI, force the bond between hydrogen and iodine to break. That's going to give us iodide anion. In addition to iodide anion, we will get protonated oxygen here, like so, with a positive formal charge on it. And now, at this point, after protonation, we recognize that the carbon atom here and here are both secondary carbons because they're each directly bonded to 2 carbons, here and here. And secondary carbons are too sterically hindered to undergo the direct attack of a nucleophile on that carbon. The carbon is too blockaded by the methyl groups for it to be effectively attacked. And so what happens instead is that the leaving group, that is the carbon-oxygen bond, is going to break as the next thing that happens here. So second step of this reaction is that we could call this the leaving group leaves. And we do that by breaking a CO bond. And that's going to give us a carbocation intermediate. So now we're into the Sn1 type portion of this reaction. So let's go ahead and draw out our protonated organic intermediate, like so. And what will happen here is that we're going to go ahead and take one of those carbon-oxygen bonds. It doesn't matter which one since they're totally symmetrical. Break it. The electrons from it are going to go onto the oxygen like so, and that's going to give us an alcohol, isopropyl alcohol to be specific, as well as a secondary carbocation, like so. Now, carbocations are prone to rearrangements. In this case, though, there is no way to rearrange this secondary carbocation, but that's something to be on the lookout for. So I'm going to put a little annotation here to watch for possible carbocation rearrangement. And that would be the case if there's an adjacent methyl group or an adjacent hydrogen that you could move over via a methide shift or a hydride shift to convert this secondary carbocation that we've created into a tertiary carbocation. That would increase the stability of it and therefore be a favorable step. But we don't need to do that here because there's no way to rearrange that. And so now continuing on, a carbocation. As a result of this step, carbocations are relatively unstable. So continuing the Sn1 type theme here, what will happen is that the nucleophile attacks that carbocation. And what we have available to act as a nucleophile in this reaction mixture is the iodide anion that we liberated during the first step of the reaction mechanism, all the way up here at the top. So that's going to come in, use its lone pair of electrons to attack the carbocation. So we put positive charge there, and the iodide comes in, acting as a nucleophile. It attacks the positively charged carbon like so, and that's going to create a new carbon iodide bond like this, giving us alkyl halide product. And that's going to be one of the final products of this reaction, so I'll circle that in gray. Now, keeping in mind, when we were doing the Sn2 reaction mechanism, what we did was, after we had created an alcohol product, that alcohol product then was subject to an iteration of nucleophilic substitution itself to convert the alcohol group into a halogen atom. And that's going to be the case here as well. So now we'll start into kind of the next chapter of this mechanism, where in step 4, what's going to happen is that now there will be protonation of the alcohol. So I'm going to draw that isopropyl alcohol. That was what we had created up here in step 2. And that alcohol group is subject to attack by and reaction with the HI. And so therefore, that's going to react with our proton. Specifically, the oxygen is going to act as our base atom there, attacking the proton from HI to give us our protonated intermediate, which I will draw out here for you. So we're going to have OH2, load pair of electrons, positive charge, and iodide anion resulting from that step as well. So now zooming out just a bit so that I can get all of the info in here. Step 5 is going to be that the leaving group leaves. So we're going to break the carbon-oxygen bond just like we did back in part 2 here, or analogously to what we did in part 2 here. So I'm going to redraw my organic intermediate, plug in that positive formal charge. The fact that this is water as a leaving group makes this a very capable leaving group and allows this reaction to proceed. So we break that bond between our oxygen and carbon. That's going to create a carbocation. Positive charge here, water as our other product of that step. And then finally, as step number 6 of this progression, what we will do is in step 6, we're going to have the nucleophile attack the carbocation. So this is analogous to step 3 above, where we have our carbocation we'd created iodide anion back in step 4 up there. And so that iodide anion comes in and participates by acting as a nucleophile, meaning it's coming in and attacking the electrophilic carbocation to make a new carbon-iodine bond and giving us our final alkyl halide product as a result of this reaction. So I'm going to go ahead and circle that for us so that we have that to keep in mind there. So the net final product of this reaction is if we take diethyl iodide, which we had up top here, we react it with an excess of HI. What's going to happen is both of these carbon oxygen bonds are going to break here and be replaced with an iodide in place of the oxygen there. Now, what would we do in this situation where we have an asymmetrical ether? And specifically, we have groups on each side that are different types of carbon. So for example, a secondary versus a tertiary carbon. So we could do an isopropyl group on one side, a tert-butyl group on the other. If we were writing out the mechanism for this reaction, and we'll do it with HBr, how is it going to go? How do we decide what order to break the carbon-oxygen bonds in? Are we going to react the left hemisphere first here with the isopropyl group, or is the tert-butyl group side going to react faster? So let's take a look at the mechanism to dissect what's going on here and use the logic that we know about molecular stability and reaction mechanisms to determine the order of steps of this reaction. So I'm drawing out our ether reactant. It reacts with HBr in the protonation step. So we're going to go ahead and protonate our oxygen atom just like we've done in the last mechanisms. That forces the HBr bond to break, and the electrons go onto the bromine to make bromide. So I'm going to put my bromide in here. And then my protonated intermediate, like so. Proton there on the oxygen. And now in step 2 of the mechanism, which I'm going to carry on with right here, just to abbreviate things a bit, we're going to have the leaving group leave. And we need to decide here, we have 2 options. One option is that we could break the carbon-oxygen bond here to create a carbocation right at this position that I'm circling. The other option is that we could break the carbon-oxygen bond here to create a carbocation right here where I'm circling. The route that we want to take here when the leaving group leaves is you want to make the most stable carbocation possible. So we're going to make the most stable carbocation that we can here. And when we say make the most stable carbocation, remember that the stability of carbocation is that a tertiary carbocation is more stable than a secondary carbocation. And so therefore, when we think about which side to break from, the side that we want to break from is this right-hand side because that's going to create, as a result, a tertiary carbocation. Whereas if we broke from the left side instead, that I'm showing with the laser pointer here, we would create a secondary carbocation. Tertiary is more stable, so we want to make that more stable product. That is going to be the faster route through this part of the reaction. And the reaction is going to take the path of least resistance, the fastest route through. So that would result, by using the blue electron pushing arrow, we'd create our alcohol that I'm showing here. We would also create a tertiary carbocation that I will go ahead and draw right here. That tertiary carbocation then is going to be attacked by the nucleophile. So I'm going to list nucleophile attacks. So we show the iodide anion coming in. It attacks the carbocation like so to create isopropyl iodide like this. That's going to be one of our final products. And then what will happen is that the alcohol that we've shown here, that will continue on. I'm not going to show the full step-by-step mechanism. We just did the mechanism for this exact same type of situation in the last example. So I'm just drawing a couple of arrows here to illustrate that ultimately that alcohol group is going to be converted into our alkyl halide, so that we would have a alkyl halide right here. And then I'm going to jump back to the lower left-hand corner here because I should have actually had another methyl group there because our starting structure here had 3 methyl groups from that tert-butyl cation. And once that tert-butyl cation picks up an iodine, it's going to have that 4th methyl group there. So our 2 final products will always correspond to the breakage of the carbon-oxygen bond right here in the upper left-hand corner is where I'm looking now. Break that bond, replace it with the halogen. Break the other bond, replace it with the halogen. That gives us our 2 main products. So if you're asked to give just the major organic products of this reaction, you could just imagine breaking here and replacing with the halogen, and that would do the trick as well. But the mechanism I've outlined here, and you want to keep in mind that what we're illustrating for this example is that when we decide what order to do things in, if we can make the leaving group leave to create a stable carbocation on one side that's more stable than the other, break from that side that will result in the creation of a stable carbocation in the first phase of the reaction, because that's going to be the fastest way for things to go, and the fastest way is going to win. Now to finish up, we'll look at one additional scenario, and that is, what about the case if you have an ether where one of the 2 carbon atoms is not an sp3 carbon. Remember that for nucleophilic substitution to occur, that is Sn1 and Sn2, occur at sp3 carbon atoms, not at sp2 or sp carbons. And so therefore, if we have a situation where we have an asymmetrical ether molecule and one of the 2 carbons is an sp2 and not an sp3 carbon, that carbon-oxygen bond is going to remain untouched. It can't break to yield a nucleophilic substitution at that location. So let's highlight what we would end up with as our product of this reaction, where we react with, we'll do HBr for this particular example. So I'm going to go ahead and erase that designation of this being an sp2 carbon just to clean things up a bit here. So what will happen in this reaction is that first and foremost, since we have an acid present, we're going to protonate. Always protonate first. Proton gets picked up by the oxygen. That's going to result in our organic intermediate here, drawing my abbreviated form of the aromatic ring. Lone pair of electrons on the oxygen. Hydrogen on the oxygen as well. Put on our 2 methyl groups, our positive charge, our bromide anion. And now at this point, when we think about which of these 2 bonds to break here, this carbon-oxygen bond or this one, it absolutely has to be the one on the right, because if we broke the one on the left, we would end up with a carbocation at an sp2 carbon. That is not suitable for nucleophilic substitution, and so we have to break from the one on the right, because Sn1 or Sn2 for that matter is not going to happen at an sp2 carbon. So leave that carbon-oxygen bond on the left side intact. No matter what's going on there, if it's an sp2 carbon, it is not going to react. So we break that bond as I'm showing in red. That's going to result in the formation of phenol and our secondary carbocation right here. And then phenol at that point is done reacting. It doesn't matter how much of an excess there is of HBr. The phenol could pick up a proton here, but that carbon-oxygen bond is not going to break to get up a carbocation and nucleophilic substitution because it's an sp2 carbon, not an sp3 carbon. So we could go ahead and circle that as being a final product of this reaction, no matter how much of an excess of HBr there is. Still going to stay as phenol. So then what will happen is that now that we've created a carbocation is going to get attacked by the bromide anion that we have made. So bromide anion comes in, attacks the carbocation, and that's going to create our alkyl halide product of this reaction. And I'll go ahead and circle that. So mechanism here, analogous to the last couple of examples we did. The key that you have to keep in mind is that this reaction will stop after just one breakage of the carbon-oxygen bond and replacement with the halogen because of the fact that one half of the molecule has an sp2 carbon directly bonded to the oxygen rather than an sp3. So keep that tidbit in mind as you're working through problems and learning this material, that whenever you're thinking of nucleophilic substitution, make sure that it's an sp3 carbon that you're breaking away the leaving group from. Otherwise, it's not going to work out.